This is AEM 637 problem 5-4.18, and this is what I refer to as one of these dam problems. And so it says a dam or retaining wall is subjected to a linearly varying pressure. P is equal to P naught Y. The slice shown in the figure is assumed to be in a plane state with all quantities a function of x and y only. So we're looking at two-dimensional elasticity. We're also looking at small deformations and so forth. Write down the stress boundary conditions for the faces OA, BO, AO, BO. I'll probably end up writing that down as OA, OB. On the basis of part A, write down the simplest area stress function that will ensure satisfaction of the boundary conditions. Explain your choice. And then let the body force of the dam be rho g in the y direction. So we account for gravity. Include the effect of body forces determined explicitly in terms of known quantities, the complete expressions for sigma x, sigma y, and tau xy. Note that the body force rho g is derivable from the potential function v is equal to minus rho g y. All right, so there is a lot going on in this problem, and some of these can be a little bit difficult. We're asked to find the Airy stress function based on what this looks like, but we'll be able to use our experience and some of the things that we've been doing in class and reading about that'll get us pointed in the right direction, I think, at least. Before we get into that, let's look at part A and talk about the stress boundary conditions. I also want to talk about the resultant forces that act on the bottom of the dam as well. And so if we look at that first, then there are a couple of reactions that we'll get on the bottom surface of this dam. Now this goes from A to B. Now this isn't what the question is asking for, but this is something I do want you to know. There will be a force that goes horizontally to resist the resultant force from this distribution. There will also be a bending moment that acts on the bottom surface of this dam that would tend to go over that way. Well, how do we find the value here? All right, so over here on this side, if the function p is equal to p naught times y, then the value at y is equal to L should give us the pressure on this end of P naught times L. All right. The area of this triangle should give us the resultant force. So let's call this V and we'll call this M. The resultant force should be equal to the area of the triangle. So it's 1/2 the base times this thing at the end, P naught L. Okay, now the P naught here doesn't have the same units as what you might see in beams, so be careful with that. All right, it just has different units. So this would be an area stress and not a force per length like you might see in beams. The resultant moment of this would act equal to the resultant force, which acts 1/3 from the large end of the triangle, times that resultant force. So the moment resisting that would be L/3 times the resultant force, 1/2 L P naught L. All right, so you may approach other problems where they may not have this particular setup for this distributed load P, or essentially a pressure P. So be careful. So this in this problem is a force per area, and then we're turning it into a force per length by multiplying it by the length to get to this end over here, and so forth. So if that doesn't make sense, stop and talk to me, and we can talk about that in more detail. But I do want you to know what the resultant force and the resultant moment would be on this kind of problem. Well, now let's look at the stress boundary conditions on the faces. And I haven't mentioned it yet, but we've been using it. The coordinate system on this problem is a little unusual. So notice here that the x-axis goes this way and the y-axis goes down this way. There are two faces that we want to look at the boundary conditions, OA and OB. Let's look at OB first. It is subjected to a linearly varying pressure. So the stress in the x direction should be equal to minus P. But minus P is equal to P naught times Y for the equation. The minus sign in here. There is no shearing stress that goes up and down. Tau xy is equal to 0. Now let's take a look at the boundary conditions on OA. All right, in general, when we talk about boundary conditions for stresses, we're talking about tractions. We remember our traction condition. T is equal to sigma n, or if we want to use subscripts, T sub I is equal to sigma ij nj. Now, our book may use the symbol boldface sigma n or something like that to indicate the stress vector. The stress vector and the traction vector mean the same things. I learned it as the traction vector, and that's what I say, and that's what I use in my notes. If you read our particular book, it probably says the stress vector. To me, that's a little bit too confusing, although it is on a stress boundary condition, but it's not the same as the stress tensor. Well, in general, in this particular plane problem, the stress tensor will be two dimensions, and it will look something like this: sigma x, tau xy, and sigma y. We also need the unit normal to this incline, and here we have to be a little bit careful. Okay, here's the unit normal, points off in this direction. How do we get there? We go over a little bit in this direction, and we go a little bit in this direction. If this is the angle theta, we need to figure out what the angle theta is in this picture. Here is the parallel slant. Here's the angle theta in this picture. Then this would be the angle theta right here. And this distance would be a sine theta distance. And then this distance would be a cosine theta distance. But let's be careful. If we start here and we want to get to the tip of this arrow, we go sine theta in the x direction, but we go minus cosine theta in the y direction. So our unit normal here is going to be sine theta minus cosine theta. Now the other thing that we can say is that on this surface of the dam, it is traction free. So the total stress vector is going to be 0. It's going to be the 0 vector. The traction vector will be 0. So traction vector is equal to stress times the unit normal, but we know that that's going to end up being equal to 0. Let's explore this just a little bit. Let's expand these equations out. So on the first one, we'll take the first row times this column. We get sigma x sine theta minus tau xy cosine theta is equal to 0. We're going to get tau xy sine theta minus sigma y cosine theta is equal to 0. Now we can play around with these equations in several different ways, and we're going to go ahead and list them out. I'm not sure at this point which one we'll need. But let's solve for tau xy from both of these. From this equation, it says that tau xy would be equal to sigma x, and then we'd have a sine over cosine. That would be a tangent theta. Now from this other one, we can also solve for for tau xy, and that would say that that's equal to sigma y, and then we would have a cosine over sine, so that would be a 1 over tangent theta. We can even equate these two. If they're equal, then let's see what we get. Sigma x tangent theta is equal to sigma y over tangent theta. So I guess we can also say that sigma y is equal to sigma x tangent squared theta. Okay, and all these things are along OA. Alright, so that would be part A. That's the information we need for part A. Okay, now this is where it gets a little complicated, and we'll work through it. On the basis of part A, write the simplest Airy stress function that will ensure satisfaction of the boundary conditions on OA and OB. Explain your choice. Alright, so here's where we need to think about what we've done so far. It says here that sigma x is a function of y. So when we think of Airy's stress function, we know that when we take the second partial of f with respect to y twice, we get sigma x. And if we want a function of y left over, we should be looking at a polynomial solution that has at least order of y cubed in it. That'll also take care of this. And since sigma y is equal to sigma x times tangent cubed, tangent squared theta, that ought to take care of this one as well. Alright, now let's look in our book, and I want to show you something from there. So let me pause this video. Alright, so here's a shot out of our book. We're talking about polynomial stress functions. Then the well-known solutions, we got y squared, y cubed, x squared, x cubed, xy, x squared, y. We got all those different things. And so basically, maybe we can take this up to the y cubed, and maybe we even want to have the x y cubed in there. I'm not sure yet. So what I'm going to do is I'm going to write down a polynomial, and then we will see if we can find the coefficients that go in front of the appropriate terms, so that when we're left with our appropriate boundary conditions, we get what we need. Hopefully that makes sense. Okay, so let me clear off a little room, and hopefully we'll be able to save what we need to save somewhere handy. Alright, so I've written down the most general polynomial that we can have that gets us to a constant times y. We don't need the xy in the end. Alright, now the other bit of information that we need are our relationships among the stress components in the Airy stress functions. So if you remember, sigma x is equal to the second partial of f with respect to y twice. Sigma y is equal to the second partial of f with respect to x twice. And tau xy is equal to minus the second partial of f with respect to x and y. And sometimes the way I will write this is I'll just say the second partial of f with respect to x and y is equal to minus tau xy. Kind of depends on how I get this set up and when I get the partial derivatives. So the next thing we'll do is we'll take partial derivatives of f, and we'll see what all these expressions are. And I'll definitely need a new page for that. Alright, so let's take some partial derivatives. Keep an eye on me. We'll start with the partial derivative of f with respect to x. So I'm going to have an a1, 2a3x, an a4y, a 3a6x squared, a 2a7 xy and a8 y squared, and that should be it. But what I really want is I want the second partial derivative of f with respect to x. And so for that, I'll have a 2a3 plus a 6a6x plus 2a7y, and that should be it. Okay, now that one is going to be equal to sigma y. Alright, so I've taken the partial derivative of f with respect to x. Let me at this point take the second partial derivative with respect to x and y. So I'm going to start with this one. I'm going to take the partial derivative of that with respect to y. I will get an a4, a 2a7x, and a 2a8y. Now that will be equal to minus tau xy. Alright, now let me take the partial derivative of f with respect to y. I'll get an a2, an a4x, a 2a5y, an a7x squared, a 2a8xy, and a 3a9y squared. Alright, so hopefully I did all that right. Let's take the second partial then with respect to y. I should end up with a 2a5, a 2a8x, and a 6a9y. Let me check my notes, and I think that appears okay. So that all of that would be equal to sigma x. Okay, so now what we're going to do next is we're going to look at our boundary conditions, and we're going to see how we can use those boundary conditions in the best way possible to figure out what all these a's are that are left over. Let's kind of make a note of what is left over. So we got an a3, an a6, and an a7. We got an a4. Okay, we got the a7 again. We got an a8. And here we've got a 5, there's an 8, and there's a 9. So altogether it looks like we have 7 things. Do we have 7 boundary conditions? Let's hope so. They might be a little hidden in there with the information that we've got. But let's see what we can start with and go through this. All right, let's. I guess I might have enough room over here. All right, so on OB, we said that tau xy is equal to 0. Maybe we ought to start with that one, because that sounds pretty nice. Now, remember, OB is the line of x is equal to 0. So let's write down what we have for tau xy. And now I'm going to put all these minus signs through on the other side. It's equal to minus a4 plus 2a7x minus and then we'll have a minus 2a8y. Now, if tau xy is 0, you might think, well, the only way we can get that is if all these things are 0. But remember, we're on the line of x equals 0, so we can say that a4 is equal to 0. And we can say that a8 is equal to 0. But we really can't say anything about a7, because when we plug in x equals 0, that this term goes away over here, and we just can't determine that yet. Hopefully we'll have another condition that we can use that on. Alright, so that seemed fairly successful. Let's take a look at the sigma x stress on the line of x is equal to 0, so that means on OB. So sigma x ought to be equal to minus p naught y. We said that right up here. Okay. So when we go to look at sigma x, that's this one down here, we have 2a5 plus 2a8x plus 6a9y, and then we know that's going to be equal to a minus p naught y. Now again, we can look at this and equate coefficients. There's no constant term over here, so a5 is equal to 0. a8 cannot be determined at this point. And the reason why is because we're on the line of x equals 0. But we can say that if we equate this side with this side, 6a9y is equal to minus p naught y. So a9 is going to be equal to minus p naught over 6. Alright, I'll need to make a little bit of room, and then we'll have to deal with the other boundary condition, which is what's going on the face OA. Okay, so one last comment before we leave this page. I just indicated over on the left-hand side what each of these terms were here. Alright, so let me clean this up, make a little bit of room, and then we'll take a look at the surface OA and see what we can find out.